Okay, so this is called implicit differentiation. Now, everything you should have ever been taught about differentiation required y to be by itself. Were you ever taught any techniques for avoiding y being by itself? Even if it wasn't in this many words, you should have basically been taught about something called getting it ready for calculus. Like, that's not ready for calculus. Or at least it wasn't when you were first doing AdMaths or Core 2. You had to expand it, right? And then it was ready for calculus. This wasn't ready for calculus. So you did some algebraic manipulation until it became ready. Yeah, etc., etc. We probably got so in the groove of emphasising this that we never actually mentioned that one needed to be by itself, but it clearly did. Yeah, not anymore. Okay. Implicit differentiation is a technique for getting dy dx without having to get dy by itself first. Okay. So let's do an example where I hope you agree. You don't have any skills, no offence, that will enable you to get y by itself there. If that was a squared, you could maybe do some tricky with the quadratic formula, but since that is a cubed, I just don't know anything. Okay? Right, so here's the funky trick. What you do is, in the privacy of your own working, you pretend that y was equal to tan x. Okay, I'll explain why that's clever in a second. Okay? So this is complete pretense, right? Of course y isn't equal to tan x, or at least there's no reason to think that it is. Okay? And then what you do is, you go dy dx equals sec squared x. Yeah? And now you rewrite the question in terms of this substitution that you've just made. Now what you do is you treat that as 5 separate questions. Differentiate that, differentiate that, differentiate that, differentiate that, differentiate that. And just stick plus signs in between your answers. Or an equal sign. Derivative of that is 0. The derivative of that is 3 sec squared x. The derivative of that is 3 tan x squared times sec squared x. You cool with me using the chain rule that fast? Alex, you cool with that?
Yeah.
Liz, you cool with that? Emma?
Yeah.
Emmy? Ellen? Elvira? Yeah, we cool? Right, now, this is the answer. And now you get dy dx by itself by factorisation. I'm going to skip a step here if you don't mind. So that's it. Okay, so we got dy dx in the end by basically regarding it as a question with 5 separate derivatives to work out instead of just one. Okay, is everyone cool with that? Want to see another example? Yeah? In this example, I'm not going to do this thing here. I'm not going to get dy dx by itself. The reason why is that we don't actually directly care about what dy dx is. Okay, so I'm going to do 3 derivatives here. I'm going to differentiate that, and differentiate that. Here's the funky trick. Pretend y equals tan x. So dy dx equals sec squared x. In which case, that's not a squared, so it's 4x tan x squared plus 6x squared all over tan x equals 10. Okay, here are my 3 derivatives. That's the easiest one. That's a 0. You comfortable with me doing the product rule and the chain rule in the same breath? Okay, so whenever I do the product rule, I always think of it as being fair. Each thing gets its chance to be differentiated and each thing gets its chance to be left alone. So first I'm going to leave that alone. Then I'm going to differentiate that. Now the other way around. Now I'm going to leave that alone and differentiate that. Is everyone cool with that? You sure? I just used the chain rule there. Yeah? Are we really cool?
Yeah.
Now I'm going to use the quotient rule. So first we write the bottom, then the derivative of the top, then the other way around with a minus sign in between. All over the bottom squared. Is everyone cool with that? Right, now, I told you I wasn't going to... Oh, I've got to get my dy dx's. Now, getting dy dx by itself there won't be that bad. Probably a bit of factorisation will be involved. But the reason why I don't actually have to do it is that this technique was part of a larger problem. They actually wanted the value of dy dx. They didn't directly care what dy dx was itself. They wanted it 1, 1. So substitute it now. It'll make it way easier. Tell me if I'm wrong. I'm going to do all these substitutions in my head. And then you get dy dx by itself there. Basically you substitute so that you can do equation solving on numbers instead of on algebra. Okay, well there's 2 examples. Now, before I do a third one, if you want me to, can somebody explain to me what is the funky trick? What does it do? I mean, what can you describe it? What is it that I'm doing?
You do it all in terms of x, so you can differentiate.
Yeah, that's why it's easier.